Hi guys, welcome back to the channel. In this video I will cover the aldehydes and ketones topic of the A-level chemistry curriculum. So let's begin. So first, looking at the oxidation of aldehydes and ketones, so you need to know that the reagent is acidified potassium dichromate. So don't forget the acidified in there, that's a key term. So the conditions for this reaction can be distillation or reflux, and we will look onto that in a bit. And the observation for the oxidation, if oxidation does occur, what you observe is the solution turning from an orange solution to a green solution. So if you're looking at primary alcohols, they are just oxidized to aldehydes, and this is done by distillation. And when we form these aldehydes, these can be further oxidized to carboxylic acid, and this is now done by reflux. So if you had a primary alcohol and you just left it under the reflux, it would at the end ultimately form carboxylic acid. So then we move on to secondary alcohols. So these are oxidized into ketones, and this can be done under reflux conditions. And just to remind you that the tertiary alcohols are not oxidized into any of these, they're just not oxidized. So now looking at the test tube reactions for the aldehydes and ketones. So first, looking at the Tollens reagents. So if the aldehyde is present in the sample, you could use Tollens reagent, and if aldehyde is present, then a silver mirror forms. And another type of test is Fehling's reagent. So if aldehyde would be present, then a blue solution would turn into a brick red precipitate. So this is if the aldehyde is present. And for ketones, if the ketones are present instead of the aldehyde, then you say that there will be no visible change. That's a key term, and you can use this for any reaction where there is no change that's visible. So you just say there will be no visible change. So looking at the equation for oxidation of propan-1-ol, so we have CH3, CH2, and then CH2 attached to that alcohol, and then we can add a oxidizing agent which will be for example potassium dichromate, but we don't really need to write the whole potassium dichromate thing down. We can just write in square brackets O, and this will represent our oxidizing agent, and this makes it much easier. So remembering the oxidation is the gain of oxygen or just the loss of hydrogen. So in this example we are losing hydrogen. So so we have CH2 there. So one of the hydrogens would go on to form H2O. So we would have CH3, CH2, and then there would only be one hydrogen in this example, because from a single bond OH, we are forming a double bond O in this example. So we write CHO, and we don't write COH because this can be mixed up for an alcohol. So we tend to write CHO, and then we just work out what's missing. So we have one alcohol there, one oxygen, I mean, sorry, and we have one hydrogen there and one there. So we just form H2O. Next, looking at ethanol, sorry. So that's a aldehyde which is formed, and if it's oxidized, it'll turn into carboxylic acid now. So that'd be CH3, CHO, and then plus again, the oxidizing agent can be represented as O, and this would go on to form the carboxylic acid, ethanoic acid, and this is the equation for this. So now looking at the reduction reaction for aldehydes and ketones. So the aldehydes can be reduced to primary alcohols. So from primary alcohols, they can be oxidized into aldehydes. So now this is the opposite reaction. and the ketones can then obviously be reduced to secondary alcohols. And for when you had the oxidizing agent, that could be represented as square brackets O, and the reducing agent can be represented as a H inside the square brackets. So there are two types of reduction reactions that can occur. One is non-selective, and the other is selective. We will be looking at both. So starting with the non-selective reduction, so this is where the hydrogen is acting as the reducing agent. So what happens is the reaction occurs if we have the hydrogen, so H2, added across a double bond in presence of a nickel catalyst. So just remember that there is a nickel catalyst involved in this. So what happens is, for example, if we have aldehyde, so you can have aldehyde or ketone. So in this example we have propanol. So this would, remember that the aldehyde is reduced to a primary alcohol, so we just form propanol in this example. Again, writing the equations down, looking at the equations. So what we do, so if we have the aldehyde propanol in this example, we just add H2 to it, and we end up forming the primary alcohol. So in this example, CH3, CH2, CH2, OH. So this is the reduction reaction, and this time looking at a ketone being reduced. So this will be a secondary alcohol now. So again adding hydrogen to it. So CH3, CH, and then in brackets OH. So there's an alcohol, but because it's in the center, we just tend to add brackets around it. So there is our secondary alcohol formed, which is propanol. So however, because it's called non-selective, what it means is that it can reduce other double and triple bonds as well. So what we want to reduce is that C double bond O, but what it tends to do is reduce any double bond. So what this means, it can reduce other double bonds such as alkenes or any triple bonds as well. So for example, in this example we have propanol. So we have two double bonds in this. We have C to C double bond making an alkene, and C double bond O making it an aldehyde. So what can happen is that both of these bonds will be turned into a single bond basically. So we will have CH2 CH CHO, and this time hydrogen again, and we would form CH3 CH and CH2 CH2 and OH. So we need 4 hydrogens in this, so just to balance it out we would add 2 hydrogens. So this is why this is non-selective reduction. So the next type of reduction is the selective reduction. So in this example we tend to use NaBH4 or sodium tetrahydroborate. So this is a reducing agent, and this is dissolved in methanol. So before we had that nickel catalyst, but in this is dissolved in methanol. So this is not non-selective, this is selective, and in this only that C double bond O will be reduced. So for example, we have again CH3 CH2 CHO. So what happens in this? So we don't need to write the whole NaBH4 down. What we can just write is the H representing the reducing agent, and because this is a aldehyde, this will be reduced to primary alcohol. So we can just write CH3 CH OH and CH3. Now because there are 2 hydrogens gains, we can just say that there's 2 of these, and for the next bits. So we have the ketone. So again, we have the reducing agent, and again balancing this, we would just get CH3CH, OH, and then CH3. So this is being reduced to a secondary alcohol, and to balance this we just add 2 at the front of all and the reducing agent. So now this is, because it's selective, it won't reduce that C double bond O. So writing the equation down for this, for example, we would ignore the C double bond O. So we're just adding the reducing agent again, and so we ignore that. So we would still have that CH2 double bond O, CH, CH2, CH2, and then that OH. So we are only reducing this carbonyl group. We're not reducing the double bond, and to balance this, again we add that to H. So this is selective reduction. So you need to be aware of the nucleophilic addition mechanism. So addition reaction in chemistry, what it means is two reactants basically forming one product. So you need to be aware of the mechanism of nucleophilic addition, especially NABH4 dissolved in methanol, reducing aldehydes and ketones. So looking at the reaction now, so for example, if I have ethanol, so I have two carbons, that hydrogen. So what happens is that I get a hydride ion first. So hydride ion has gained a electron, and it has a negative charge. So this, because it has gained that electron and it had that electron already, so it has a lone pair now. So what happens is that lone pair, so the carbon and oxygen, remembering that oxygen is one of the very electronegative elements. So this is a very electronegative bond, and this means that the carbon is a electropositive bond. It has a partial positive charge. It's delta positive charge. So what happens is the lone pair from the hydride ion is attracted to that carbon, which has that partial positive charge. And what this does is that the double bond, so the double bond between that CO is broken, and that's the electron is given to the oxygen. So now looking at the next step, so we have that carbon again. So because we have gained this hydride ion, we have we had H at the start, so now we have two H's. So one H is there, the other one is there, and then that CH3 again, it's remained there, nothing's happened to that CH3. So now what's happened to the O, because it's gained that oxygen and that electron from the double bond, so now it has a negative charge and it has a lone pair of electrons because it's gained that electron from the double bond. And now, so we have a H plus coming along. Remember that the NABH4 is dissolved in methanol. So methanol is an acid, and we have a hydrogen ion coming from that. So we have that H plus, and we, from that lone pair now, we are attracting that hydrogen ion, and at the end we end up forming an alcohol, because that O and H combine, forming that bond. So we form ethanol in this. So we have gone from ethanol to ethanol. So this is the nucleophilic addition reaction. So you're required to know a little bit about the hydroxynitriles from the specification. So you need to know that when KCN, so when potassium cyanide reacts with aldehydes or ketones, followed by dilute acid, so it can be any dilute acid, sulfuric acid, or any other acid. What happens is that the hydroxynitriles form. So now HCN is extremely toxic. It's very, very toxic, and it can be very dangerous to add HCN directly, carbonyls directly. So if we can't add HCN directly to aldehydes or ketones, it can be very dangerous. So what we tend to do is we put KCN, so potassium cyanide, in the reaction mixture, which has that aldehyde or ketone or that carbonyl group, and we add sulfuric acid, so H2SO4 to it, to form the gas. So we can that would end up forming HCN, and that can be used in the reaction. So it can be very dangerous to form to add HCN directly, but we can end up forming HCN from doing a reaction involving KCN and H2SO4 in the reaction mixture. So you might be asked to draw the nucleophilic addition reaction now with HCN. So it's the same process as we covered in the NABH4, so the sodium tetrahydroborate, but it's just HCN now. So we will have ethanol again. So it's to the carbon attached to double bond O, CH3 and hydrogen. So this time we have that carbon attached to that nitrogen. So remember that carbon, this would be a nitrile bond, so it's triple bond CN, and then this carbon is this would have a charge at CN minus, so this carbon has a negative charge, and then it would also have that lone pair. And so again, it would be attacking that carbon because it has that partial positive charge, and that would be donating the electron to O. So oxygen gains an electron. In the next step, we again have that CH3 attached to that carbon, but this time we would have that oxygen, which will have gained an electron. So now it has a positive charge, and it will have that lone pair now, and then that hydrogen from there, just following on, because we're adding a dilute acid, so we will have a H plus again. So this lone pair in the oxygen will attract that H, and we will end up forming this molecule. So this will contain a nitrile. So this particular molecule would be called 2-hydroxypropane nitrile, because we meant to name from the carbon containing the nitrile. So first carbon, second carbon, third carbon, we have the OH group on the second carbon, so that forms 2-hydroxypropane nitrile. So enantiomers. So during a reaction, the nucleophile can attack carbonyl group from either side as its planar. So if you're looking at the molecule containing that carbonyl group, so this is the carbonyl group, and if you look from the other side, this again is the carbonyl group. So the nucleophile is able to attack from either side. It can attack from, so if we say the hydride ion is the nucleophile, it can attack from this side, or the hydride ion can attack from the other side. So it has an equal chance of attacking from both sides. So what we say is that there is an equal chance of a nucleophilic attack from above and below the planar groups, planar carbonyl group. And what this means is a mixture of enantiomers are produced by aldehydes and unsymmetrical ketones. So now I mentioned unsymmetrical ketone. Now this is because, for example, if we have a symmetrical ketone, so for example pentan 3-on in this example, so if the carbon attached to the double bond O is attacked by a nucleophile, on both ends we would have C2H5 on one end and C2H5 on the other. But if you remember the definition of an enantiomer, it has to have 4 different groups attached to that carbon. Now, because it has 2 same groups, it cannot be classified as an enantiomer. So that's why it has to have unsymmetrical ketones. So what happens, because the carbonyl group can be attacked from above and below, and there's the equal chance of being attacked from above and below. So an equal amount of both enantiomers forms, and usually we end up forming a racemic mixture. So remembering what a racemic mixture is from the optical isomerism topic, it's a 50-50 mix of both of the mixtures, but both of the enantiomers. So we end up forming that. So in this example, with the cyanide, with the potassium cyanide, so these are the 2 enantiomers that form after the reaction has taken place. So looking at the final thing, the rate of reaction of aldehydes and ketones. So ketones generally have a slower reaction than aldehydes. Now this is because of 2 reasons, but mainly one that we focus on, which is the inductive effect. Now, because ketones have 2 alkyl groups, whereas the aldehydes have only 1 alkyl group. Just looking at just imagine the shape of a ketone, because the double bond is in the middle, so there's 2 carbons attached to it. So I can call this CH3. So these are basically 2 alkyl groups. So alkyl groups, just any carbons attached to it. So these 2 carbons, what we can consider as alkyl groups. But aldehydes only have 1 of this. Aldehydes, because the oxygen is at the end, we only have that 1 carbon attached to it. So aldehydes only have 1 alkyl group. So what this means is that alkyl group release electrons towards the delta positive carbon. So that carbon, the CH3 or whatever it is, it releases electrons towards the delta positive carbon, which is attached to that double bond O, and this reduces the size of the partial charge. And because ketones have 2 alkyl groups, therefore they have a greater positive inductive effect, and therefore the bond is slightly less polar. The carbon to oxygen double bond is less polar, reacting more slowly. So looking at the actual picture, so this would be a aldehyde and this would be a ketone. Ketones, the C double bond is in the middle. So because it has 2 alkyl groups attached to it, so there's more positive inductive effect. So as you can see, the partial charge on the carbon is smaller, but on the aldehyde, because there's only 1 alkyl group, the partial charge is bigger, and the more, so this means that the C double bond O in the aldehyde is more polar, and that's why it can react faster, and therefore the reaction is faster with aldehydes. So there's also the steric effect. It only came up in the exam once, but this is the alkyl change causing a hindrance during reaction. So this is in ketones, and this prevents the nucleophilic attack. So compared to a aldehyde where the C double bond O is at the end, because ketones have it in the middle, it makes it harder for the nucleophile to access that C double bond O, and this is one of the reasons why the ketones then react slower than aldehydes do. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.